Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit where we're going to be talking about Euler's Totient function. Now we'll get into what that counts and what that does in a little bit, but let's get started with a little bit of review. Now this review isn't super important for today, but I just want to get us in the mindset of kind of a counting question. So we've seen this before. If you're given the prime factorization of a number, you can do a lot of things, including things like count the number of factors of that number. So if you have the prime factorization, you add 1 to each of the exponents in that prime factorization and multiply them out, and that gives you the number of factors we have in total. So using that prime factorization, you can kind of turn that prime factorization into the number of factors of the number. So you could define a function that way if you wanted to as well. We're going to look at something slightly different today, dealing with relatively prime numbers. So quick review of the definition. Remember, two numbers are relatively prime if their greatest common divisor, their greatest common factor is 1, right? They have no common factors at all except 1, which is a common factor for any two numbers. As some quick examples here, 20 and 5 are not relatively prime. Of course, if we have a factor of 20, it's not relatively prime with that 20 itself. Things like 9 are relatively prime. 20 is, 2 squared times 5. 9 is 3 times 3, so the only primes that the only number they have in common is 1 there. 20 and 15, just to be a little bit careful. You don't have to have, you don't have to be a factor to be relatively prime. 15 is not a factor of 20, but 5 is a factor of 20 and 5 is a factor of 15. So those numbers are not relatively prime either. Going back to our definition, just kind of one little quick reminder here, reminding ourselves that the GCD is 1 means they're relatively prime. A common mistake people make is the number 1. 1 itself is relatively prime with any other number. Because of course, for example, the GCD of 20 and 1 is 1. So that is kind of called relatively prime, even if it equals the number 1 itself there. Okay, so getting into the topic of the day, we want to kind of be figuring out how many numbers are relatively prime to a given number. So we have the number 20, and we want to count the numbers from 1 to 20. So it's kind of like factors, right? So if we have 20, what are the factors of 20? Of course, all of those factors are between 1 and 20. Relatively prime numbers could be bigger than 20, right? 21 and 20 are relatively prime. We'll do an example with that later. But for the counting we're going to be doing here, we only want to consider the numbers, the integers, from 1 up to 20 in this case. So I said, of course, 1 is always relatively prime. So let's just kind of list out the numbers that work here. 1 is relatively prime. 2, all of the even numbers are not. Remember, it's not just factors of 20. We have to get rid of 2, we have to get rid of 4, that's correct. But we also have to get rid of 6, because that has a common factor of 2. 8, 10, 12, any of the even numbers are not going to work here. 20 is not divisible by 3. It doesn't have any 3 in its prime factorization. It does have we got rid of the 4 already. 5 is a factor of 20, so we have to get rid of 5 and 15 and stuff like that too. 7 is relatively prime. Of course, other prime numbers are relatively prime. But 9 also works. We saw that in the previous slide too. Like I said, primes 11, 13, 17, and 19 all work as well. But remember here, my final kind of question is how many are there? And so there are 8 in total here. So we have 8 numbers from 1 to 20 that are relatively prime to 20 in this case. Now, we could list them out. Sometimes you will need to list them out or figure out which numbers there are. But a lot of the times, you might just be curious about this counting question. How many are there? And this is actually exactly what our topic of the day does. The Totient function, this is also called the Phi function. So it's written as phi of n. It's equal to the number of integers from 1 up to n that are relatively prime to n. Right? So this is exactly what we did in the previous example then. Right? So it's either called the Totient function or the Phi function, and it's written with phi, right? So that's where the phi name comes in. Officially, it's the Totient function, but right, sometimes you'll hear it talked about as the Phi function, and it's kind of defined as counting up the number of relatively prime integers from 1 to n for that number n in this case. So just want to stress one last time, it is another counting question. Just kind of like the number of factors, but here we're counting the number of relatively prime integers in this case. Now, some examples. We just said phi of 20 is 8, right? So for 20, we have 8 of these relatively prime numbers that we just saw, 1, 3, 7, 9, 11, 13, 17, 19. Another good one to think about is, what about a prime number? Right? It shouldn't be too hard to figure out that phi of p is p minus 1 for a prime p. Why is that? Because if p is prime, every number 1, 2, 3 up to p minus 1 is relatively prime with that number. Right? So these are some of the examples we kind of already saw and are easier to think about there. When we get to bigger numbers, this is not as easy to figure out, and the patterns are a little bit harder to try to list out all the relatively prime numbers, but luckily we have a formula we can use here as well. Now, we're not going to prove this formula, but right, it is good to kind of look at it, and we'll practice using it a little bit today. And again, just like the number of factors, phi of n can be calculated if you know the prime factorization. So if you have the prime factorization of a number, you can calculate phi of n by taking the number itself and then multiplying it by something for each of the prime factorization factors. So we have p minus 1 over p1, and then we have p2 minus 1 over p2, all the way up to, so this is done for every single one of these primes in the prime factorization, all the way down to p minus 1 over pk minus 1 over pk there. So right, this is kind of getting rid of multiples of the p1, p2, etc. This formula is a little bit more complicated than you may think. We're not going to do an official proof of anything here, but this kind of formula is very, very helpful. And you can kind of look at this as, right, the total number, and then we're kind of doing some ratio type stuff for each of the primes in the prime factorization. Now, one little thing, right? I listed the prime factorization here, but notice that the exponents don't matter. So really, you can think of this as phi of n only depends on the distinct prime factors of n. That might save a tiny bit of time, right? You don't actually need the full prime factorization of the number to calculate phi of n. You just need to know, right, which primes divide the number there. just as a quick kind of sanity check here, let's look at phi of 20. So we've calculated this already. This should be 8, but according to our formula, it's the number 20 itself times, and 20 is divisible by 2 and 5. Those are the two primes we look at. So 2 minus 1 over 2, so that's 1/2. And then 5 minus 1 over 5, so that is 4/5. And so then multiplying this out, of course, we have 20 divided by 10 is 2 times 4 is 8. So this does work and does match perfectly what we had before. Just getting used to the formula a little bit, let's look at a few examples to kind of practice this as well. Now the first one, we can do the prime factorization in our head, hopefully, right? So 75 is 3 times 5 squared, 3 times 25. So phi of 75 is just going to be 75. It's divisible by 3. So we have times 2/3 in this case. And then we have times 4/5. So, right, when you're kind of getting used to this pattern and getting comfortable with this pattern, right, you can kind of start always having the p minus 1 in mind for those prime factorizations in the numerator. So we have 75 divided by 15. That's how I like thinking about these usually. So that is equal to 5, and then we multiply it by 8, and so we get 40 there. 2020, let's just remind ourselves really quick, right? So for example, if we want to write out the prime factorization, 2020 is 2 squared, so it's 4 times 5, so that's 20 right there, times 101. And 101 is a prime number in this case. So here we have 2020, so full number, and we can multiply this by 1/2 because we have our prime factorization including 2. We multiply by a 4/5 because our prime factorization contains a 5, and we multiply by 100 over 101. So this number here is going to be a little bit bigger in this case. So we have 100 over 101 here. Now, remember that prime factorization when doing the kind of multiplying as well. Because if 2020 is 2 squared times 5 times 101, everything in that is going to cancel with the denominator, and we're left with a 2. 2 times 4 times 100 is 800 here. So there are 800 numbers from 1 to 2020 that are relatively prime with 2020, right? So you wouldn't want to have to do that by listing things out, right? Patterns are a little bit complicated there, right? So this is really an easy formula to use and is pretty helpful when you're looking for relatively prime numbers and how many of them there are. Let's look at then one application to finish up. We'll see some other applications in a later video, but right now let's look at this kind of question that really is about relatively prime numbers. So we did 75 just a second ago. So let me just kind of remind ourselves of that, right? We just did on the previous slide that phi of 75 is 40 in this case. So we're going to kind of do an example using that fact and talking about how this is a little bit more powerful than you might initially think. So suppose numbers relatively prime to 75 are listed out in a sequence. Now, remember, phi of n doesn't count all the relatively prime numbers because that's impossible, right? Going above 75, we still have relatively prime numbers. So we have an infinite sequence here, right? We're listing out all of the relatively prime numbers. 1, 2, right? 3 is not. 4 is. 5 is not. 6 is not. 7, 8, 11, right? We're listing out all of these relatively prime numbers. And we want to find the 125th term in this sequence. So even if it's not immediately clear how to start, let's kind of see what the phi of 75 tells us, right? We have our sequence here, 1, 2, 4, dot, dot, dot. Now, if we think about 75, right, 75 isn't relatively prime to 75, but what about 74, right? 74 is, right? 1 less than 75 is relatively prime to 75. So in fact, right, we know that 74 is going to appear in this list. Now, something even more that we know is that this is 40 in total, right? So this is 40 terms right here. So we can kind of jump ahead in a sense, by kind of saying, okay, phi of 75 being 40 tells us that we have 40 terms in total from 1 to 74. Now, here's where things are a little bit more powerful than you may think, like I said. Well, remember some facts about GCDs. Well, what about 75 plus 1? Right? 75 plus 1, because it's 1 more than 75, that's going to behave exactly the same as 75, right? Or 75 plus 1 minus 75, which is 1. Right? So actually, for each of these 40 relatively prime terms, if we add 75 to them, so if we kind of take these numbers and add 75 to them, we're going to get a whole nother list of 40 terms. So we have 76, we have 77, we have 79, all the way up to, right, 74 plus 75. So this is 150 minus 1, 149 in this case. So we actually here have then another list of 40 terms as well. So here we can kind of start seeing a pattern in this case, right? So let me just kind of do this again. We can kind of see the same pattern there. I'm not going to list out all of the terms in this case here, but we have 151 up to then, right, here we have up to 75 times 3, so we have 225 minus 1, so this is 224. So this is another 40 terms in this case there. Now, the key thing is, well, 40 plus 40 plus 40 is 120. So now we have 120 terms in total. So we need how many more? We just need 5 additional terms in this case. But wait a second, we can still get these 5 additional terms by adding 75 to the previous ones. Or if you like, we're adding 225 to the beginning of our sequence. So, right, the 121st term is going to be 226. The 122nd term is, right, 227, right? So we're taking our original sequence and making it bigger and kind of adding these numbers to it there as well. So we have 232 and then 233. So this one kind of is what we want in this case. This is going to be our 125th term in the sequence. Now I know the numbers kind of worked out nice in this problem, but I just kind of wanted to give this as an example and kind of show you how this kind of pattern helps in kind of general situations where we might be looking for relatively prime numbers and things like that as well. Right, just a little summary of this number really, really quick. Remember, kind of the shorthand way then is that this number is 8, so the 5th term in our sequence, plus 3 times 75 there. Because we know 40 terms occur every 75 numbers, so we're kind of shifting up 3 times and then getting our 5th term in the sequence there. thank you guys for watching. Like I mentioned, we will revisit Euler's Totient function and look at some other examples with it in a later tidbit. So if you enjoyed this video or are looking forward to that one coming up, please like this video and subscribe to the channel here. And check out ziml.areteem.org for daily math practice and other resources that can really help you improve. Goodbye.